Okay, your bell ringer is, what are the three parts of the force spring model, and how are they addressed in this particular equation? Uh, when a student usually hears what's the force spring model, what they typically do is they go, oh, it's an equation, they write it down. Okay, there's more depth to that, and we need to understand that a little bit better before moving on. Next, let's say you have an object. Okay, there's an object, there's a box, there's something. Pick an object. I don't care.
Cat.
A cat. Okay, so it's not a box anymore. It's a cat. All right. Nailed it. Okay, and the cat is being pushed down. Okay, by somebody's hand with they're pushing the cat down with 23 newtons. The force of the person is 23 newtons. I'm going to say the mass of the cat is 5 kilograms. Sorry, handwriting. 5 kilograms. What is the force normal on that cat? Okay, again, what are the three parts of the force spring model? And how are they addressed in this equation? Number two, if a 5 kilogram cat is being pushed straight down with 23 newtons of force, what is the force normal on that cat? Go. Don't do numbers right away. Those of you that just grab calculators, do the work. Do the work. That's what I'm more focused on more than anything. I'm only going to give about 3 minutes to go through this, so please write the stuff down. Brianna, this is you.
Yeah. I'll still be here, guys.
Yes, please.
Can I take the test sometime this week?
Sure. You can take a break.
Sure.
Okay.
right, let's work through this. This first part of the spring model, and how is it addressed in that equation? Yes.
There's three parts I think are amount versus stretch.
Well, let's begin. Let's take it one piece at a time. What does that mean, amount versus stretch? See, like, some of you might have just questioned my logic on Friday, thinking that, like, why did he spend an entire day teaching us 3 equations, one of which were actually 4 equations, 2 of which we're never actually going to use? Why didn't he just throw the equations on the board? I mean, literally, it's right there. Just throw that on the board. Let me use it. Why did we spend so much time doing it? Because you have to understand these models on a more intrinsic level. Okay, so what does that mean? Force amount versus stretch.
I think that it means
Go ahead.
like how much the spring is stretched. Like it could be 1 inch, but then if you stretch the spring out, then it's not 1 inch anymore.
Sure, it's not quite what we're looking for, actually. You've got a right idea. I appreciate you saying an answer that you didn't know it quite right, because that is very important in here, guys. It is beyond important. It's so important to learn physics for you to sort of get over yourself and be like, hey, we've worked with everybody in here. We know nobody has the right answers. Say wrong answers, okay? Try to figure it out. Come to terms, okay? I said this the first hour as well, and this is my big struggle with kind of your guys' class right now, is that, like, some of you guys are very smart, but you're very smart based on the system that we do here at school. And the system that we do here at school is like, hey, here's the right answer, write it down. Okay, I'm gonna write it down. I'm gonna write it on the test. This is the right answer. I need you guys to figure out difficult stuff. And difficult stuff means you don't know. You don't know the answer. If you did know the answer, why the heck are you here, right? Like, if you could learn the answer in 5 minutes, why are we in school, okay? Why are you taking a class if that class doesn't teach you anything, and you just learn it in like 5 minutes anyway? Like, you could literally just read a book at home and in like an hour be caught up on an entire class as like week or 2 weeks of work. That class is pointless, utterly pointless. So, you don't know. Let's get over ourselves and just answer out. What do you think?
Force spring is proportional to.
What is that's fancy talk? I hear you. You're not wrong. What does that mean?
It's the same.
It's not.
It's like opposite.
It's not.
No.
The force spring depends on the displacement from the equilibrium.
Yeah, and you kind of know that, right? Like, look, how much is the spring currently pushing? 0. How come? It's not stretched. It's at equilibrium, right? I mean, you didn't use that word before. Like, if you were, I need you to talk about this to a certain degree in just basic words. Like, and if you struggle with springs, you don't need a lot with springs. How about a rubber band? Okay, you dealt with a rubber band before? Okay, here we are, a rubber band. How much force is the rubber band currently putting out? None. It's not stretched. You want it to put out force. What do? Stretch it. Okay, so you stretch it a certain amount. Okay, so tell me what to do with the spring to model exactly what we're talking about right now. This amount versus stretch. What should I do with this? The rubber band. Stretch it more. What does this now tell us? Now that I've stretched it more, what would you're not holding it in your hand, but you would know what would be the case if your hands were holding it right now. What's true of your fingers now? It's pulling more and more and more and more. Yes, it takes more oomph to hold it here than it does to hold it here. Right? That's all it says. Stretch it more, it should be pushing more. Okay, and that is addressed by what part of the model?
Okay.
Not quite. What'd you say?
I think the Fs and delta X.
Yes, these are the first power. Okay, they're proportional, like you said. Or what that means is, if this doubles, then it's double, or triple, or half, or half. They go together. They increase and decrease together. Stretch it more, it pushes more. There it is. What else? What's the next part of the model? Direction. Okay, what is that meant by direction? Well, let's look here. Which way is the spring being pulled right now? Let's focus on one side, because obviously you can technically argue by or not. Let's focus on my left hand, as you see on the right now. Okay, which way am I pulling the string? To me, it's left. To you, it's right. Let's focus on your perspective, okay? To me, this hand is pulling right. Yes. Which way is the spring pulling? Left. So technically, if delta x is positive, then force spring is always, and vice versa, right? If I push this spring in, right, now the delta x is which way? To your left. Which way is the force spring pushing? To the right. Yeah. Okay. I'll come back to that here in just a second. What's up with the K? What's the K do? What does it do? Why is it there? What is K?
Spring coefficient.
What is that? Spring constant, technically, but what is it?
It's the difference between one spring compared to another, as in material wise. So like one spring could be made up of a more harder material to like pull out compared to another spring. So it's like the type of force that you would need to stretch it farther.
Yeah, you got the right idea. Okay. K, if you look mathematically, is the ratio between these two right here. Yes? Anytime I say ratio, you should always know this statement. Ratios are never the point. Ratios help you to get to the point. Let me talk about another ratio you're very familiar with. Velocity. I tell you that a velocity is faster. What does that ultimately say mathematically? What it says is, for a certain time, the faster one will cover more delta x. Yes? Or, for a certain displacement, the faster one will take a smaller amount of time, right? Velocity is never the point. We want to look at how far it goes or how much time it takes. Same thing is true here. What is true if we deal with this kind of car spring or this shocks that are over here? This is, in case you can't tell from perspective, about a ½ an inch thick. Okay? Earlier you just saw me taking this spring and stretching it like, well, let's go with about, 4 or 5 centimeters. If I had this thing in person right here, which I should, it's only $3. I can get a 6-pack. Anyway, if I had it right here and I attempted to pull it out 5 centimeters, what would, you're shaking your head? No. What do you mean you're shaking your head? Why are you shaking your head? No. Because it's not going to go. Why is it not going to go 5 centimeters? Exactly what you're saying, right? It's the same thing. Either for the same delta x, which is what I was trying to argue, 5 centimeters, you're correct. It would take an insane amount of force, or much more likely, for the same amount of force that Spainhour is able to put out on his muscles, delta x isn't going to be nearly as much. That's all it does. The K represents the different strength of the spring and represented by a ratio. Okay, one more thing to address here, and then we'll move on to that last one, is this. So, I talked about direction a second ago and why that negative is there. That being said, there are certain times in physics where we could make this model is more accurate by putting the negative there, but you go like, is it really helping us? For example, if I took this spring like this and I said focus on the bottom, my left hand here on the bottom, which way is force spring pulling? Up. Did any of you do that mathematically in your head? Did any of you go, well, delta x is negative, and therefore force spring better be in a positive direction? Or could you very easily intrinsically see that the arrow on this thing better be up? The second one, yes? So that negative is probably going to give us more difficulty than it's going to help with, right? Like, if I have, again, if I have a spring hanging from like a ceiling or like the bar that I did on Friday, we know force spring is up on that force diagram. We don't need to do any math whatsoever. So this is the reason why the AP equation sheet does not have this listed. It has this. That's supposed to be an equal sign, my apologies. Okay, and all it is saying that the magnitude of force spring is simply equal to K times delta x in this particular case. Don't worry about the negative. Feel free to not use the negative when you're doing your work on stuff. You can go ahead and just use this right here. Honestly, even if you do happen to write this right here,
I'm going to go ahead and assume that you mean the absolute value. That being said, you do need to know this for the test and what the actual full model is, but definitely mathematically, just go ahead and use something like this. All right, let's head over here. I've been dealing with a lot of emails, not dealing with, that's not the right way to say that. I've been seeing a lot of emails from students that are, I don't know how to do this, and I'm finding the same thing when I look at their work or answer their work. And a lot of times we're not going to the two main places that I start all of these problems. And I don't think that's like laziness or lack of intelligence or anything like that. I think the major issue that you guys kind of have to, again, somewhat get over is this. It's that problems are now getting bigger than your brain is comfortable with, and you guys like problems when you can track and know every step between the beginning and the end. And when you don't have that familiarity with you, it's uncomfortable. And when it's uncomfortable, you just stop and you don't take the next step. What I'm warning you is this. I talked about this at the beginning of the year. I'll use this analogy again. If you have a puzzle in front of you like my 2-year-old son does, okay, with the numbers laid out, you don't need any strategy. You don't need any strategy whatsoever. You can easily, confidently look at the whole thing and finish it in about 30 seconds. You know where it goes. You don't have to think about it. If I then laid in front of you a 1,000-piece puzzle and said, hey, where does every piece go? All of you would intelligently look at that and go, that's stupid. There's no way to know immediately where there's way too many things to keep track of. The same thing is true of problems when it comes to math and physics. Problems are getting bigger. And if you only ever look at problems and are saying, I will only do a problem if I know all the steps, you're shooting yourself in the foot. You have to just know what comes next. What comes next in physics? Fall back on Jafib's. The first thing that you should do is the given and the find. Within the given, the next step is force diagram. If you're not drawing force diagrams, I don't know what to do for you. So even when problems, I see this too. I see students doing simple problems and they're not doing the right steps. They're not doing it because I don't need to do this step. I don't need to do this step. But then when the problems get more difficult, they go, I have no idea what to do. Yes, because you haven't been practicing the right steps. So what do I mean by the right steps? Force diagram on this cat, what you got? Force gravity down. Wait on force normal always until the end.
Force of person down.
Force of person down. And the reason why you wait on force normal until the very end is now I want to ask you, should force normal be bigger, equal, or less than gravity? Bigger. How big should force normal be? Same as the combination of those two. Correct. I don't care if it's perfect, by the way. Again, not going to get out a ruler, but I do want to very clearly see, I will take off a point on your test if you draw it like this, where force normal is pretty much equal and opposite to gravity. Now, if you make it any bigger whatsoever, it's pretty obvious it's bigger, then yeah, we're good. That's first. What's your very next step?
Given.
No, we already did that. You could do that separately, but I'm going to say that's not the big thing that's next. After you've done your force diagram, what big thing is next? Sum the forces in the x, sum the forces in the y. If we're not doing this, again, this is the next step. Always, 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 always. Now, it's a representation of vector addition, so you might have been getting away with just kind of doing vector addition, looking at this and going, hey, force normal has to equal those two. Perhaps that's what you're doing. But again, you're going to see today, problems get more complicated. You're going to want this particular step in place. So, sum the forces in the y equals mass times acceleration in the y. And what do I mean by summing the forces in the y? Okay, it's that thing that we did when I said, hey, here's A, here's B, here's C. What are the sum of forces in the y? Now, when you do it like this, everybody's pretty basic to go and ask the same questions that we always do. Is it in the y? What direction is it in the y? Is it only in the y? So up here, actually, I'm going to change this last one. Hold on. Okay. A, is it in the y?
Yes.
Positive or negative?
Positive.
Is it only in the y? So you say positive AY. It's there because it's in the Y. It's positive because it's up. We put the Y because technically I'm not looking at this arrow. I'm looking at that arrow right there. Okay? Next, B, is it in the Y? No, leave it alone. C, is it in the Y? Yes, is it only in the Y? We're done. You do the exact same thing when you look at these. Force normal, is it in the Y? Positive or negative? Only in the Y? Yes. You probably don't need me to do the rest, but this is what you should be doing. Next question when it comes to summing the forces after summing the individual forces is it accelerating in the Y? No, the object's not accelerating in the Y. So we cancel this, and this is equal to 0. Now, how would you find force normal given that equation?
You already know force person, and you have enough information on force gravity.
How do we find force gravity?
Do mass times the gravity.
Now, me personally, you can do what you want. Addie suggested a second ago that we calculate force of gravity ahead of time. You are welcome to do that. Go over to the side and then just plug in. Okay. My personal take, and again, it really doesn't matter, whatever you're comfortable with, is I like to plug in right here. So this is mg plus fp, which is going to be 5 kilograms times g plus 23 newtons. That should be like 49, so it should be 72 newtons. Again, that would have been 49 if you'd calculated it separately. Can confirm? Does it make sense that the ground is pushing more than gravity? I would argue a couple of reasons on that. Why does it make sense? What's that?
He's not the only one going or
So you-
adding on it down.
You can talk about it mathematically in terms of vectors, 100% agreed. That's one answer. The second reason is think about what force normal actually is. Force normal is the electrons of one surface pushing on the electrons of the other. So why would the force normal on the cat technically increase in that light? By pushing the cat down, the electrons have gotten closer, and now force normal is going to increase. How are we doing? All right, let's move on. So, I apologize for not being here yesterday. Illness at home wasn't mine, but it didn't matter. I had to be there for kiddos. So, since we weren't here yesterday, and I still would like to put the test on Monday so that we don't, you don't want to wait an entire break before taking this particular test. It's going to be painful for you. I'm going to get rid of the lab that's on Thursday. The rest of the time before Monday is just prepping these type of problems over and over again. Trying to understand Newton's 3 laws a little better, trying to understand this process. So there's no new. There is absolutely no new whatsoever. It is just working on these type. Well, I shouldn't say that. It's sort of a new type of problem we're going to introduce today, but ultimately, yeah, I think you'll be okay. All right. So let's begin with this. We have a box on a table. Box is so lame. Let's say it's a box of monkeys. Inside, there's a bunch of monkeys in here. Okay, I don't know, but just putting a box seems really dumb. I don't know, it's just so basic. I don't care. Anyway, the mass of the box is 30 kilograms. Okay, now 30 kilograms is a very large box. Okay, let me put this in perspective. The 50-pound weight that you've seen me throw around out here is 22 kilograms. Okay, so a 30-kilogram weight like this is about 70 pounds. Okay, so this is a very, very heavy box. Okay, we're going to tug on this 30 kilogram box. We're going to push with the force down like, let's go. We're going to push the force down like this. So we're going to push underneath. Now, to give you an idea, this will be, let's call this tension. So we're going to use a rope here. It'll be 100 newtons. And then this angle, it's going to be below the horizontal 30 degrees. Oops, my apologies. I screwed this up. The mass, I'm going to change the mass. I changed the mass last hour too, because I didn't want 30 and 30. So let's go ahead and call it 20. My apologies. So I said it was a 70-pound box. That's like, that's roughly a little bit less than a 50-pound box. All right. The coefficient of friction is 0.15. And the question is, how much does this box accelerate? Now let's put some context so you can see this.
Here I have a yo-yo on the table. So the way you could get this situation in real life would be like you could either push this down at an angle, like if you would imagine like somebody sliding something shady across the surface. Okay, they're pushing kind of down at an angle, or it's a little bit hard to represent here. But if I'm talking tension, this person is technically pulling it down into the ground, like right down here. Now, notice even though they are pulling down, is the object actually going in that direction? No, because of other forces at play. So, draw the force diagram up there. Give you about 30 seconds to do that on your own. And then we'll get going.
Is that FT?
Yes, force tension. It's a rope. A rope that's pulling. So somebody is pulling that giant box. If you want, it's a big box of monkeys, and someone's pulling down at an angle. So they're not pulling perfectly horizontal. All right, what forces should be on here?
Force gravity down.
Force gravity straight down. Now, oops, my apologies. I wanted this all the same color here, so let's just go back to force gravity.
And then your force tension already.
What's that?
You have your force
Yep.
tension already. So your force normal should be the vector addition of both of those.
Correct. So the question I was going to ask that you've already answered is: should force normally be bigger, equal, or less than force gravity? Should be more.
Why is force normal?
Because there's two forces in the Y. There's this one, and then force tension. Even though it's over here, the way you should look at a force that is at an angle is kind of like this. Here, I'm not going to keep this up here because I think it's going to get messy. This right here is force tension in the Y. This is force tension in the X. Okay, so you can see that it's also acting in the Y. Now, usually when we draw this, we don't draw it like that, although it's kind of helpful to see it that way. The way we usually draw it is like this, so that we can better understand the trig that gets us to those particular answers. But it's fine to draw force tension in the Y either over here or over here to kind of help you to see that. All right, we're missing one more force.
Force friction.
Force friction goes which way? Straight back. Not opposite of tension, opposite of the way it's moving. Okay, so you don't know what you're doing. Let's just, maybe you do, maybe you don't. Let's pretend you don't. You've done your given and find. You've done your force diagram. What's next? Summing the forces. Okay? Where do you want to sum? No, let me ask this question. Which way should it be accelerating? The X. Okay? Just going to ask that and then ask you, so where should we sum our forces first? Sure. Okay. Now, I'm going to warn you ahead of time. I'm going to tell you that that's actually not going to work out, but I do want to start there because you don't know that. Okay? You don't know. You're just looking for the answer. And this is not a bad place to start at all. So, what are the sum of forces in the X?
FTX minus FF.
Agreed. That's acting in the X, but not only in the X. This is acting in the X in the negative direction and only in the X, and the other two, neither of them are in the X, so we're done. Once you've done the sum of forces in the X, answer the typical question, is it accelerating? Yes. So we leave it alone. Now, if you're just new to this and you're like, I don't want to see if I can do this, just run through like, can I get this? Can I get force tension in the X?
Yes.
Yeah, you can use trig, right? We know that the hypotenuse here is 100, and we would get that with trig. Can I get force friction? Do I know what force friction is right now? No. So I know force tension in the X, or I can get it. I know mass, I don't know force friction, so that means I'm not going to be able to get acceleration. So we need to go well then how the heck do I get force friction? Remember this guy right here from Friday. What is mu equal to?
Is it force friction over force friction?
It's a ratio. And like I said earlier, if you hear a ratio, you should think ratio is not the point. The ratio means if I know one of those, I can get the other. Now, so far in our problems, the x and the y correctly are kept entirely independent. But force friction is typically on the x, and force normal is typically on the y. So this guy sort of combines the two of these together, aka if I want friction, what can I go get to get it? Force normal. So to get force normal, what do we need to do? Let's sum the forces in the y. All right, what are the sum of forces in the y? Fn minus Fg minus Fty. And is it accelerating in the y? No. So that cancels, and the whole thing's equal to 0. And if I do my algebra on this, what you'll notice is this is the exact same thing as the bell ringer that we did today. All right, how do we get force of gravity? Correct? How do I get force tension in the y? A little bit more specific now. Sine, correct. You have the hypotenuse, you have that. Again, I want to reiterate to you, sine does not anymore automatically go with the y. Sine is always opposite over hypotenuse. The reason we're using sine is we want the opposite of that angle, but that angle is not always going to be given to us nicely. So this is going to be force tension times the sine of 30 degrees. Or this is 20 kilograms times g. Sorry, my kilograms are all sorts of wonky there. Times g plus 100 units, newtons, sine of 30. So that's 50. That's roughly 196. Should be 246. Is that right?
Yeah.
Sweet. And why is finding force normal helpful again?
Because the mu helps us find force friction.
It's, and usually this is going to be the case. A lot of times you're going to find force normal to find force friction. There is certainly the opportunity on a problem, if you know force friction, to reverse to get force normal. That definitely does happen. I don't usually start this way. You're welcome to always start here. You're also welcome to do this very basic algebra to already have it sitting like this. Force friction is equal to mu times force normal. Mu is 0.15. Force normal is 246 newtons. So that should be 24.6, 12.3, 36.9. Interesting. All right, and what can I do with that 36.9? We go right back to where we started at summing the forces in the x. How do we get force tension in the x? So I like to set up my problem ahead of time algebraically, or just with letters first. Ft cosine 30 minus force friction divided by mass. That is equal to acceleration. Or, I'm going to run out of room here. Used to be harder to do that with the dry erase board. So this is 100 newtons cosine of 30 minus 36.9 newtons divided by a mass of 20 kilograms equals, let's see, that's 0.866, 86.6 divided by that should be roughly 50 divided, it should be about 2.5, a little less. What'd you get?
2.5.
Is it 2.5?
I I rounded some of my numbers.
Oh, okay. Yeah, around 2.5 is right. Let's do this though, real quick. Let me erase that. What about this problem changes if instead of pushing below, what if we did the exact same thing, except this time we were to push above the exact same amount? But it's above the axis 30 degrees instead of below. What would change? What's that? Yeah, well, let's talk about this though first. You're 100% right. You're skipping it. You got ahead of me. What doesn't change? Does anything in the x actually change here? Yes and no. The math, no. You're 100% right. But you're also right that what would change is that this would be positive. So when you did algebra, you would subtract. Instead of add 50, you would subtract 50. So instead of 246, it would end up as 146. Doesn't that sort of make sense? Like, think about it like this. This situation that we had before is like a wagon. It's like a wagon, but imagine you're pulling along some, like, you know, some little kids, some siblings, some nephews, some nieces, whatever. Would you pull it so that you're pulling them down into the ground? No, you're probably going to pull them up at an angle. You're probably going to pull them like this. Now notice, even though you're pulling them up at an angle, they're not actually going that direction, right? The reason they're not going that direction is because your force tension in the y is still much less than their gravity pulling downward. So they're still going to be pulled down into the ground. But what's going to change is force normal is now smaller. Since force normal is now smaller, what will also be smaller? Force friction is going to be a lot smaller. And if force friction is a lot smaller, what happens to our final answer? You'd accelerate a lot more. Now, this makes sense in the same way like we were talking about on Friday, is if you attempt to lift a very heavy dresser, right? If you try to lift a heavy dresser and somebody stupidly like jumps on top of the dresser, it's like, go ahead and move it. Man, that's not going to be nearly as easy. What are they technically changing? They're changing the force normal. They're changing how close they are. So they're also changing friction. Friction is harder to overcome. On the offhand, you shove them off, right? You get annoyed at them, okay? But you still can't pick the object up. What do? You still lift up, right? Even if it can't leave the ground, by lifting up, what happens to force normal? Decreases. And the reason it decreases is because even though it's still touching the ground, those electrons are a little bit further away, right? And now, since force normal it decreases, what also decreases? Friction, making it much easier to slide heavy things across the ground, even if you don't actually pick them up off the ground. All right, moving on to the next problem. We're probably more than likely not going to be able to finish this one today. That's okay. The idea is to get set up, and I think this also helps with a particular problem on 4.5. All right, so no. Frodo is rolling down the hill because he sees the gate open, and stupidly he thinks he can just like walk through the gate in the second film. I don't understand why he thought it's not important. Okay, if you're not a Star Wars, if you're not a Harry Potter, if you're not a Lord of the Rings nerd like me, you can just go ahead and imagine a ball rolling down a hill, or if you prefer, a box sliding down a hill like a lame person. But I'm gonna do a Hobbit. All right, mass of Frodo, what you got? 17 kilograms. How'd you get that out of curiosity? You just picked a number. Okay.
120.
Okay. Now,
Oh.
let's put this in perspective, Jalen. You're not 120.
You don't know that.
I do. I can use my basic understanding of density or average density of a human being, look at you and go, nope, not 120. You know, I know you're not 120 because I can pretty much guarantee if you stand over on that you are not 260 pounds. Okay? Pretty much. I don't know that. You're right. I'm very confident in myself here. Okay, so
Now, let's say you didn't make that guess of 17. I'm going to go in a slightly different direction because of a skill that's very helpful. Okay, you guys are probably not super comfortable with mass yet. Is that fair? But you probably would be decently comfortable if I said, how much does Frodo possibly weigh? Okay, 3 feet tall. What you got? What's that? 60 pounds?
Kilograms.
You don't get to answer anymore. You're done today. All right. How many pounds? 70 pounds? Yeah. Okay. So if you don't know mass, here is the correct way to convert. Now, if you've been in a gym, you will know that they use a standard conversion of 2.2. Okay. I don't love that because mass and weight, not the same thing. Not the same thing at all. Okay, here's what you can do. You can say, all right, let's go ahead and call Frodo 70 pounds. Okay, then you can convert to newtons with the conversion that I've already given you. In 1 pound, there are 4.45 newtons. Someone do that for me real quick. How many newtons?
15.9.
You did that the wrong direction.
My bad.
That's on top. We multiply.
308.
308. Okay. Now, first things first. There are problems.
It should be 3,000.
What?
3,000.
70 times 4.4. I did 4 point anywhere. What are we doing? It's 70. I guess on one time.
Okay, for starters, 308, not that far off, not that big of a deal. Those of you that just lost your mind over 3 newtons. Okay?
I didn't know.
Secondly, 3,000 is a no. Just a no. Okay. 312 is about right. Now, again, I remind you that a newton is very, very small. You're going to have to get over your kind of feeling of 300 pounds is not 300 newtons, okay? They're not the same thing at all. You know how much 300 newtons is? It's about 70 pounds. That's how conversions work, people. All right, now, this number here and that number here is the weight. There are times where a problem at the very beginning will not tell you the mass of the object. It'll straight up tell you the weight. And the way you'll know this is it'll say instead of it being a 120 kilogram hobbit, 260 pound hobbit, that would be magical. Okay, because the density just doesn't exist in the world today. But is just number the newtons, right? It'll say it's a 300 Newton hobbit. Okay, and you know that's weight. And if you go into like summing the forces in the y, then you do not need to use mg at all. That is the weight right there. That's like saying, this is the same thing as saying the person is 70 pounds. It's saying they're 312 newtons. That is the force that is right down there. That's 312. But if you wanted to know the mass out of that, okay, well, what equation do you use if I give you mass to find force of gravity? No, that's not what we use. Fg equals mg. Please make sure you know the difference between these equations because they look similar and they are not. So, there it is. If you have mass, you get force of gravity by multiplying by g. So if you have Fg and you want to know mass, use the exact same equation, just do a little bit of algebra here, people. How do we get the mass? Fg divided by g. Keep in mind when you use this equation, a Newton is a kilogram times a meter per second squared. So this up here better be in newtons in order to use this equation. 312 newtons divided by g tells you that it should be roughly what, 32 kilograms-ish? What do you got? 32 kilograms. So if we go with the 70 pound Hobbit, 32 kilograms. If we went with the 17 kilogram Hobbit, I think that puts us roughly in, let's go roughly half of that. So you're saying that the Hobbit is like 35 pounds, which to put in perspective is not terrible. Okay, my 2-year-old son is about 31 pounds right now, so you know it's somewhere in there. All right, moving on. Let's talk about this as well. What is appropriate angle of a hill? Like, what would you think if you were driving around? What is the largest angle on a hill that you have driven on here in Alton, more than likely? This is pretty steep hills over.
60.
There are some steep hills.
Oh, maybe that's
No. Okay, that's what I wanted to address. So people very much overestimate angles of hills because what they do, and it's rightful, you look at the hill and you go, that hill's tall. But that's it. That's all you look at. You go, that's a tall hill. And it's going to take me a lot of oomph to get on that hill, so that's a steep hill. At 45 degrees, you are no longer walking. You are not walking up a hill, okay? As a matter of fact, at 30 degrees, you are questioning your life and your choices that you are going up a hill at all. You're probably really darn close to climbing at that spot. To put this in perspective, in the United States, okay, hills need to, without any sort of extra provisions, be kept under 10 degrees.
What?
So it is surprising. That is very surprising. A lot of the hills, I'm not saying that all hills in Alton are 10 degrees. Like if you go downtown and look at some of those, I'm not saying those are perfectly 10 degrees, but I bet you those angles on those hills are way smaller than what you would expect. To help you understand this, if you've ever driven in the Rockies, okay, and if you haven't, the Rockies are mountains and they're very steep, okay? The largest, the thing that requires a sign on the side of the road that says, steep hills, be careful. Underneath it will tell you the angle of the hill. It'll say 15 degrees. In the Rockies, 15 degrees is stupid steep. So yeah, keep that in mind. I'm not saying that there are not steep hills in Alton. I'm saying that they are probably much smaller than you think they actually are. That being said, Frodo's going to roll down this hill. What's the angle of the hill?
How did you get 32 kilograms?
Oh, we just landed. I forgot. 10 degrees.
There's a video up on it, or there will be in a few minutes, so feel free to go back and check that out. All right. Anyway, angle of the hill, what do you got?
20 degrees.
20 degrees. That's a magically steep hill, but we'll go with that, okay? So we get some
Yeah, that's
significant.
what I'm saying.
Sure.
It's a magical place.
Yeah, but we're assuming basic physics. Otherwise, I'm just gonna write, what's the answer to acceleration? You're like 40, magic. Like that's probably not gonna be okay. All right. Force diagram on Frodo as he rolls down. I'm sorry, this is an incorrect picture of Frodo here. I apologize. You got the ring of power here, and he's got curly hair. Okay. Force diagram on Frodo as apparently he breakdances on his face down the hill. Or slides down a hill. And if you're struggling with like the complexity and the nature of this box rolling down a hill, we will finish this tomorrow. Please do that force diagram before you get back tomorrow.